All right, we have a different set of directions for this next section. We are asked to use the concavity test to determine the intervals on which the graph of the function is concave up and concave down. And I'm going to do a little extra too, because I'm also going to talk about how we use this to find points of inflection. So the concavity test deals with the second derivative. So the first thing that we have to do is find, of course, the first derivative. So we get y prime equals negative 4x cubed plus 12x squared minus 4. Now, if I wanted to find the local extreme values, mins and maxes, this is where I would take this value and set it equal to 0. And if you were doing this, say, on the AP Calculus test and you were allowed to use your calculator and you needed to find the zeros for this, remember, you can actually just type this into your calculator, do second calc 0, and come up with your zeros that way. You would still show your sign chart and everything else from that. And we will do problems like that the next time we have class. So we have the second derivative is negative 12x squared plus 24x. And this is what I want to set equal to 0. So I am setting the second derivative equal to 0. I'm going to factor out a negative 12x. So I'll have x minus 2. So then I get x equals 0 or x equals 2. So these are my two critical points for my second derivative. Okay, well, we wouldn't really call them critical points, but these are my two potential places of points of inflection, which is one of the things I said I was going to talk about as well. I also would need to look at where the second derivative is undefined, but again, we have a polynomial function, so it's never undefined. So I'm going to make a sign chart with my second derivative values here. So I have a 0 and a 2. And we know the second derivative is equal to 0 for those values. So then again, I'm going to substitute points on either side. So if I plug in a negative value, if I plug in a negative value here, I'm going to have a positive, and a negative value in here, I'm going to have a negative. So if I have a positive times a negative, I'm going to get a negative value. If I plug in a positive 1, so say I plug in a 1, positive 1, I have a negative times a negative, so that's going to be positive. And then say I plug in a 3, I'm going to have a negative here, and I'll have a positive in here. So that's going to make that negative. So often when I substitute in these values, I go into my factored form if I have it factored, because it's a whole lot easier than to just think about positive times negative or negative times negative, rather than plugging it in here and actually having to make more calculations. So the concavity test says that if the second derivative is negative, then it's concave down. Remember, when I say it, I'm really talking about the function y. So y is concave down on the interval negative infinity to 0, union 0 to infinity. And the increasing decreasing part when we talked about that, we included the 0. Technically here, we don't. And to tell you the honest truth, I can't really give you the reason exactly why, but I'm just going to say don't. So then, and the reason is since y double prime is negative. This justifies your answer using the concavity test. So this is important. Don't forget to say, since y double prime is negative, it's not enough just to use your sign chart. Y is concave up on the interval 0 to 2, since y double prime is positive. So that's the concavity test, how we can tell if the function is concave down or concave up. One additional thing I want to add to this is what that tells us about points of inflection. What this tells me is we have 2 points of inflection, and they would be 0. Now to find out the y value, you have to go back up into here, your original function. So you'd plug a 0 in here and you'll get 1. So at 0, 1. And the reason is because it goes from concave down to concave up. So, and the other one is 2, and I substituted that in already and got a 9. Okay, so my reason is because it changes concavity. Which, remember, means y double prime changes signs. Now that covers both directions. And actually it's a point of inflection regardless of which way. If it changes from negative to positive, that's a point of inflection. If the second derivative changes from positive to negative, then that's a point of inflection. So we don't have the kind of max or min thing, so the order of that wouldn't really matter. It just tells you that you have a point of inflection. Okay, the next example, again, same direction, so the same section, so we're going to have to start by finding the first derivative. So when I do that, derivative of that is 0, so I get negative 1/3 x to the minus 2/3. So then y double prime is positive 2/9 times x to the minus 5/3. So I'm going to rewrite this as 2 over 9, the cube root of x to the 5th. Okay, and if you think about what we needed to do first, we needed to set the second derivative equal to 0. Once again, if I were looking for mins and maxes, I would have taken the first derivative and set it equal to 0. Here, though, I'm looking for the concavity of my function, so I'm taking the second derivative and setting it equal to 0. Now, it's a rational function. To find where the rational function equals 0, we set the numerator to 0. So this is never 0. But remember, we also have to look for where y double prime is undefined. And that will happen when x equals 0. So we have a potential point of inflection when x equals 0, and that's really what we were looking for to see if it changes concavity. Now I would have to double check if you plug a 0 up into your original function. That's okay. It's not excluded from the domain because it does pass through. X equals 0 is part of the domain of my function. So I'm going to see what happens with this point. So we have y double prime, and we know it's undefined here, but I have to see what's happening on either side. So if I plug in a negative value right into here, you can take the cube root of something negative, all right? It's not a problem. So we're going to end up with a negative on that side. And if I plug in a positive value for x, then I'm going to get a positive value. So that tells me that y is concave down from negative infinity to 0, and concave up from 0 to infinity. And I forgot something really important that hopefully you're thinking of. Since y double prime is negative, since y double prime is positive, or you could say because. All right, so that also means that we have a point of inflection. Whoops. Now remember, I'm saying that y has a point of inflection at 0, and if you plug that back up there, it was 5. So at the point 0, 5, we have a point of inflection because y double prime goes from negative to positive. And be careful about your wording. Y has a point of inflection at 0, 5 because I've had students sometimes say things like y prime changes concavity, but that's not y prime changing concavity. It's y that's changing concavity. So you have to be really careful with your language and make sure that what you are saying is accurate. Okay, so that should get you through a few of the problems for the homework.